going to say just a few words, but before, and then I heard Wenbin's excellent talk, which they were mainly sort of a critique of some of the problems of some of the other models, and he said more eloquently than I could have done what problems I'd had with some of the other things that had been suggested. And then I heard Pawan's talk just now, and again, it was very similar. What I was going to say was very much similar to many of the points that he made, and so there's some similarity to that too. And then finally, I've just heard Yuri's talk, where again there's some similarity. So what I was originally going to do was sort of talk about ideas that Emil Levinson and I had a couple of years ago. In fact, we drafted a paper and so on, and then found a mistake, and it's an interesting mistake. But since coming here, and I've sort of a few more things. So this will start off, I suppose, as in your language is not a post-diction or a pre-diction, but a retro-diction. And then if what I have to say, which is not a mature thought by any means, but it sort of follows on from what Amy and I were doing, and that may turn out to be a contradiction, deserving extradiction, if it turns out to be wrong. But anyway, let me just sort of say what it is, and it's motivated very much by this sort of thought that the FRBs come from the magnetospheres of magnetized neutron stars, probably magnetized easily, and they are guilt by association and so on, because that's really a coherent emission, and they're and the view, the view is that they're rather efficient. There's not all these gamma rays. Radio astronomers are deeply sensitive people, and the faintest breeze or a slight change in temperature, and they get terribly excited and rush off papers to Nature and so on. Whereas you hit a gamma ray astronomer about the frontal lobes with a 2x4, they don't notice, and so they're deeply and so there's not much power and there's not much energy in these FRBs, which is it's a compliment to a radio astronomer, and so trying to do this very efficiently in terms of the free energy available, rather than with a lot of wasteful unseen gamma rays. And this is very much, I think, motivating things that Pawan said, and also I think implicitly what Yuri said. So I'm very much on board with that philosophy, even if it turns out to be wrong. So the idea that was inspired, as always, as ideas are, by metaphor some time ago, and there are two metaphors. One is a tsunami, which we know quite a lot about, and the other is Indiana Jones and cracking the bullwhip and so on, which actually turns out to be a much more interesting problem. Lots of underemployed cowhands write letters to Journal of Fluid Mechanics and so on, trying to explain this. So it's actually quite complicated, that one, but I think the tsunami answer better. But it's basically the idea that a relatively small disturbance, as Pawan described, caused by a starquake or a flare on the surface of a neutron star, probably, but not necessarily, but probably linear to start off with, steepens, and something that has a wavelength maybe of 100 meters or so, which would be the sort of characteristic size. So if I just do something like this, lambda of order 100 meters steepens to something with structure, say, around 10 centimeters, which is what, for the gratification of radio astronomers and so on. So you develop this structure in a steepening wave, as in a tsunami and so on, which is a long wavelength, low amplitude disturbance, which becomes nonlinear with catastrophic effects and so on. So that's the thought. and basically, the idea, let me just back up a little bit and say, in the regime here, unlike Yuri, where the inertia simply is unimportant and does not matter. So we're doing force-free electrodynamics. In an SGR, the point is to make all that electromagnetic energy into paired plasma, into gamma rays and so on with high efficiency. So not interested in that regime. We're interested in the other regime, when it's essentially just a force-free wave, force-free disturbance, and in particular on an open field line where it's just going out and escaping all the other things that might be happening alongside it. So it's the first out, and it just goes along the open field lines. Nothing on the closed field lines. Things that go backwards and forwards on the closed field lines are likely to make pairs, but that's after the show, and you may or may not see them. Okay, so basically, if you think about these waves, then in the simplest version, if you just take a linear wave like that with some wave vector like that, and it's well known there are two modes. One of them I'll call an electromagnetic or a fast mode, and it's just an unchanged vacuum electromagnetic wave, no currents, no charges. That will just go straight out of there. Nothing happens. The other mode, as Yuri explained, is an alphane or an intermediate mode, and that is one that requires currents and charges for a shear alphane wave, for an oblique wave. So it requires currents and charges. And again, you've got to ask, as Pawan did, where do those come from? So let's consider this perhaps as a disturbance. Now, as it goes outwards down the declining magnetic field, its amplitude relative amplitude delta B over B will increase. It'll become nonlinear, roughly at a radius 10, 20, 30, whatever stellar radii, depending on what the configuration of the energies and so on. So it'll come at some significant distance from the surface of the star. It'll become nonlinear, and at that point, so then the question asks, well, what happens at that point? And this is where the retroaddition comes in. What I thought, erroneously, was that the energy, any sort of front would increase in proportion to the square. It would increase on a cone, essentially, if it goes the square of radius. And I just implicitly thought that without thinking. And if you do that and just make very simple arguments, the wave, in fact, does steepen. But what is in fact the case is that it expands along the flux surfaces. So that front the area will go as r cubed. Under those circumstances, that wave, as I've just described it, does not steepen. And the person who explained this to me was Yashi Yuan, who works here. And she did some force recalculations, said we're not seeing what you expected because the wave is going out on these. And it was, it's after the fact, it's obvious. So doing the simulation certainly changed my views on this. So, but then the sort of thought that I've been thinking about a little bit here, and also very similar to what Pawan says, is you come to a point when you can no longer freshly create in the advancing front the electrons and positrons, the charges that you need to carry the currents and supply the charge density in this pulse. You can no longer do that. Close to the surface, the vacuum is essentially a perfect conductor. You can do this at will, but far enough out, you can't. And so the thought is basically the following. If we just sort of consider this, let's just, maybe green fields are green. So let's have, I'm not quite sure why that line is there. Let's start over here. Let's suppose that we've got some sort of disturbance like that. And then say these are magnetic fields, as I say, sort of like that. Here's a magnetic field, and it's going out. This is an oblique wave. So if we do it in the frame of the pulse, which you can do, and this is just for a pulse going one way, I'm not interested in things going backwards and forwards, then there's obviously some pointing. There's a pointing flux, an electric field upstream. There's a pointing flux that's going to be coming in towards the surface and across the surface, bringing electromagnetic energy in. And then you can figure out what's going on here, and this can be a stationary pulse and so on. And as long as rho E plus J cross B equals 0, it's just a completely non-dissipative alphane wave. Alphane pulse, if you like. This you can sort of describe in the frame with essentially this electromagnetic coming in. Now, if you want to say how is this going to evolve, if you think about it in the frame of the pulse, it's a relatively small thing. It's a sort of more or less adiabatic change. The first thing that happens is that these field lines ahead of the frame slowly move apart, and so you can follow the energy that way. And this is just going down the magnetic gradient. and the wave will, the pulse will change as that happens. And as I say, that was the part I got wrong, but now I think I understand. And in fact, this picture makes it pretty clear why what I said was wrong. And so it goes across like that. But then the second thing, where I think there may be some action going on, is the what Pawan called the charge starvation radius, when it becomes, for this particular pulse, not in general, but for this particular pulse, no longer possible to make the charges, no longer possible to make electrons and positrons locally. So in that case, you can sort of write down, you're going to develop essentially an E along the magnetic field, E dot B not equal to 0. And that is what is ultimately responsible for making the charges, and it's sort of written down some sort of simple prescriptions for doing the for a sort of Lorentz invariant Ohm's law in that locally in an environment. It may well be a non-local problem, but doing it in that environment. And the sort of where I'll just leave you with the following tantalizing thought, which is not something that is demonstrated. It may all turn out to be horribly wrong. But the thought is that this front here essentially moves at C. If you take the magnetic field ahead of the pulse and say the pulse is moving in that direction, some angle theta to that direction of the magnetic field, 45 degrees or something like that, then the characteristic speed is C cosine theta. So you've got to do Lorentz transformations and so on to get in the frame, but that's easy. So you do the Lorentz transformation to get into this frame, and then you write a Lorentz invariant prescription for failing to make the current that you need, to violating this condition, not with inertia, but with, as I think one of the talks said, made it absolutely clear, changing conduction current into displacement current. So it's that steady conversion. And the thought is the following. This part in the middle, where this is going to happen is this bit in the middle. And this bit in the middle, there that's where you'll start making an electromagnetic wave out of an Alfvén wave. And that is going to want to travel at the speed of light, whereas this up in front is traveling slower than the speed of light. So just like, the waves that we know, like ocean waves that in the Riemann problem overturn and become, then there's a chance that will be traveling faster than that, and will steepen it up. And I don't know whether you can get from 100 meters to 10 centimeters, but if you can, you've got some very sharp pulse. It goes out without too much. It's the elephant hitting the fly's nest, as you said, and goes out of the magnetosphere and so on, and then encounters at some point plasma, which does the dispersion and will then spread its way out. So there are many ways, of course, there are so many ways, some of which are rehearsed, that this could be falsified by observation. And obviously, if you can say that the original initial pulse has to be, say, milliseconds in length in these pulses, this one has to be something that's essentially a delta function. And then eventually it's going to be spread by all the propagation. So, and obviously finding gravitational waves or neutrinos or whatever alongside these things will rule it out. Anyway, that's enough. Okay, so okay, there you go.
Thanks again, Roger. And what we would like to do is I have posted some questions here, which unfortunately I think the panel is not able to quite see, but you will answer. We will answer a different one. Yeah. But these are just to get things started, the discussion. What I would really like to do is have questions from the audience for members of the panel, and I would like to make one suggestion, just one suggestion to the panel members. You all have got different ideas, and you have your own favorite model. For the next 42 minutes, may I just urge you to think a little bit outside of your own model, which I know are beautiful models. All of you have got beautiful model. If it is not realized by nature, well, that's her problem, not your problem. So let's get that out of the way. Okay, and for the next 42 minutes, let's keep an open mind to see what nature is doing. And I have posed here a number of questions. We can certainly The first one, for instance, is something that Estelle Finney's panel. I wasn't here but dealt with, and I'm assuming, Estelle, you have an answer. Is it a magnetar or not? But in any case, so that has been answered. Yes and no. It is yes and no. Okay, all right. All right. Okay, so that one we are not going to. Although the question of central engine and the radiation mechanism are not decoupled. One has the effect on the other. Okay, but we are not. That has been dispensed with. Okay, so we are moving on. So there are all these different ideas that we heard this morning. Masers, plasma processes, etc., etc. One question that I pose is, at what distance is the radiation being produced, assuming there's a compact object, close to the compact object, far away from the compact object? We have, again, heard arguments for and against it, yeah? So I would like to suggest that each member of the panel, maybe just for 30 seconds to 1 minute, and restrict your answers to short, brief, sharp answers, 1 minute, to this question. And also, a related question is the radio channel the dominant channel for the energy that is coming out? Or is the energy coming out, most of the energy coming out in some other channel, okay, non-radio channels, yeah, at higher frequencies? So if I may have the members of the panel here just go and say 30 seconds to a minute each, these two things, these two questions.
Don't need 30 seconds to say I don't know.
So we don't know. You can just say I don't know. That's fine. That's a totally fine and honest answer. So let's just start. I know you are. You very much are part of the theory panel.
Yeah,
but you bring one thing that none of us do. You have observations, yes. So let's start with you, Virginia.
Well, I think the clear answer is I don't know. But I am hopeful. I just find magnetars very exciting. So I think that is my guess for what they are, only because it's wishful thinking.
Ali?
So I would say that probably a useful thing to do is to try and constrain observationally the energy fraction in radio compared to other wavebands. I think that even in the most optimistic models, only, let's say, very efficient mechanism, like 1% of the energy would come out in the radio. So somewhere between 100 times and 6 orders of magnitude larger energy should come out in other wavebands. And I think this is one of the most important things to try and constrain.
You can certainly answer that question for your own favorite model. That's a totally fine thing to do, yeah? So that the audience here, and we have got good number of observers here in the audience, they get some sense of what the expectations are. I mean, that's what I'm hoping that they could carry with them. I mean, they would carry with them that theorists are all confused, no, nothing. I mean, maybe that's what it is. But so you can say about your model, for instance, what the expectations are.
I don't have a favorite model, and I think it's not the right way to go. I think that we have a large uncertainty between 2 and 6 orders of magnitude, and we need to try to constrain this observationally. There's no point in betting on some.
That's
some
fine. It's a totally fair point. So let's go. Oh yes, of course, yes. Thank you for reminding. So Shasha is online, and let's turn to Shasha.
Hello.
We can hear you.
Do you want me to answer?
Can you please, if you would?
So I don't want to bet on magnetars versus non-magnetars. I think we don't have yet enough evidence to think about this. Before I go, I want to comment about your second question about masers, plasma processes, antennas, and stuff. So I'm strongly in favor of plasma processes and with respect to bunching. I think 50 years of pulsars taught us something about bunches being not a nice model for coherent radio emission. With anything else, I'm very much fine and in agreement with.
All right. Let's move. Anything else to add, Shasha, to that? Otherwise, we'll move on to Wenbin Lu. Wenbin.
So I again, I start from the observational point, which is if you integrate over all the effort repetitions from 12, 11, 02 and average over time, it's a huge, there could be huge errors, but you get 10 to the 44 ergs, roughly, if it is not beamed, isotropy equivalent. So if you can compare that with some, total magnetic energy for a given magnetar, let's say 10 to the 15 Gauss, or it could be 10 to the 16 Gauss, which will make it more extreme. But it seems to me if magnetars are really the thing, then the efficiency is not very, very, very low. Cannot be 10 to minus 6 or minus 8. So there it depends. So my answer to the question is that depending on whether we get counterparts or not, if the efficiency is indeed high, I mean by more than, let's say, 1%, then there is a hope to get to the bottom of the story, I think. If it is very low, 10 to the minus 4, 10 to the minus 5, I think it's hopeless to get to, I mean, within the decade or so, it's hopeless to get to the bottom of the story. That's I don't bet on any other things.
If it is this low, where is the rest of the energy? Like
that's in other wavelengths.
So
it would be actually better in that sense, right? Because it would be brighter at other wavelengths.
Yes, it will be better to
We have a
constrain,
chance.
yes.
Chance to
But the actual mechanism for radio emission, we may never have the chance to get to the bottom, because that's such a tiny fraction of the total energy budget.
but it's,
Can you please use a
from the
microphone if
first
you're on the
talk,
panel?
we already have some constraints on how much other energy there could have been, right?
Not very constraining.
That's right. At this point in time,
But is this going to improve?
Optically, yes, I think, at least.
Yes, in the optical it could be improved. The X-rays and gamma rays.
By how much? So, like, what's the prediction?
In the X-rays and gamma rays, I think it's going to be a bit difficult, but in the optical it could be much improved. And I mean, we already know that in the repeater that you mentioned, the energy that is emitted in the flares in radio is 6 orders of magnitude smaller than the energy that you have in the persistent source emission. So we already know the radio is sort of.
so Roger.
Okay. So to answer your question, I personally regard 10 to the 40th brightness temperature pulses coming from a solar mass worth of nuclear matter embedded with a Schwinger post-Schwinger magnetic field, magnetic field and electric fields as being the boring, conservative, and prosaic explanation. And I'm rooting for Chris Thompson or something like that. I would like to see something even more exciting than that being the explanation. Sure. And so that's where I come from. And I would make one more thing. When the next tranche of transient event as a class gets discovered, we call them after GRBs and FRBs, we call them ERBs.
So first I have to say that this format with 1 minute reminds me of the democratic debate. So I like it.
Only limited. I wish there was more time.
No. I'm joking. I'm joking.
Limited
just say
by
that I feel kind of like Bernie Sanders.
Available.
So a couple of points that I just want to make. I think so. What I gather from this, from our discussion this morning, is that we all love coherent emission processes, and regardless of everything else, this will be a very good excuse to understand more about coherent emission processes in astrophysics. What will have to be done carefully, I think, in any case, is the details of why this emission process get to work and it's persisting. For example, in the case of the charge bunches, are we actually sure that there are no competing mechanisms once the charge starvation regime is achieved that will destroy the charge bunches before they actually have the opportunity to radiate? So I think especially the multidimensional physics of the process might pose challenges or might open new avenues for investigation. I think the other point that I think is worth a serious consideration is that these are very strong waves propagating in and I'm making this as a very general statement, these are very strong waves propagating in very exotic environments, and we really need to understand very well the propagation of these waves, and that will potentially discriminate very seriously whether they're coming from very close to the engine or further away, and whether this is actually a way to distinguish these possible scenarios.
Thank you. Well, Lorenzo, the point of the charge clump survival is, of course, something that has been around, and they will survive on a time scale of order of the light crossing time across the clump, which is something on the order of R over gamma. Just to clarify that point, but let's move on to Yuri.
Hold the mic.
Okay. I would like to mention that from my point of view, all this classification, maser emission, plasma, and what else, antenna, is more or less the same. Because it's just different language of description. Because what has been maser? People describe on quantum language that there is inverse population and so on. But we deal with classical system. Therefore, all these systems are, in fact, unstable plasma, with some resonance stability. And if wave is appropriate resonant frequency enters, it is amplified. And then it is amplified modulating plasma, and therefore bunches are formed which radiate these waves. Therefore, this is also antenna emission. There is no the difference is that in maser mechanism, bunches are formed naturally. In what is called antenna emission, bunches are formed by some other mechanism at the best, or in many cases just by inserted by hands. And this is
Can you hold the microphone closer so they can hear you on the internet?
Okay, and this is the basic problem with what is called antenna mechanism, because this is just hand waving argument how these bunches are formed. And my concern about all these stories about curvature emission of bunches and so on, even taking apart all question how these bunches are formed, how they survive against huge repulsive potential. When people use formulas from Jackson's textbook, it looks very suspicious because they assume that this is radiation in vacuum. But if we believe if we believe that these bunches are created by little green men, this is okay. They produce these huge charges and send them. If we believe that this is produced in plasma, we know that plasma density is determined by the condition that the number of particles per bunch, so plasma density, should be large enough. Specifically for FRB, we need plasma density such that plasma frequency is orders of magnitude larger than the emitted frequency. And in this case, Jackson's textbook should be, with all respect, put apart, because this is different radiation. It's radiation in plasma. Plasma shields charges. And the first question should be answered: how charge, assuming that this charge is formed, radiates in this plasma?
Let's go to Anatoly and hear from Anatoly. And let's also turn to audience. I think instead of kind of addressing all of these questions, which are interesting questions, let's just follow and have everybody an opportunity to answer and raise questions. So we do, I see that. Let's just go through
let me just
Anatoly's view.
Talk a little bit about the coherent emission that we actually observe, and we think we should understand better, which is the one coming from pulsars. So there has been some development in the last year based on the ab initio simulations of magnetospheres that people like Sasha Filipov are doing. So there seems to be two mechanisms that are creating coherent radio emission from pulsars like the crab. So there is the polar emission, which we all know and love, but there are also things that we call giant pulses. And so the giant pulses seem to be in these current ab initio models to appear from beyond the light cylinder. They seem to be coming from the current sheet, and they seem to also be coincident with gamma rays. In that region, what's causing them in the simulations is reconnection. So reconnection, as was shown in several talks, creates these islands, and those are large conglomerations of charge. And when they merge, that's a global perturbation to the electromagnetic field. And that's, you know, if you want to call it bunch, you could, but it's really just a change in current. So two islands colliding. So if I wanted to bet, I would bet on some sort of islands of currents colliding somewhere. I don't know where. From aesthetic point of view, I prefer being close to a neutron star rather than very far away from it, because it seems like it's more under control. Like if you want to repeat it, it's right there. It's much easier to repeat. If you have to rely on something very far away, a lot of fine tuning, just from aesthetic point of view, seems to be needed. Another radio emission that we know is the polar one, and this is where some advances have been made recently. The traditional picture that there should be some as these bunches of emitting curvature radiation. We don't see that in simulations. What we do see is time-dependent gaps. So there is an accelerating field close to the star. It accelerates particles. Gamma rays are produced. Those gamma rays create pairs, and they short out accelerating electric field. The way that shorting out happens is not one-dimensional. It's two-dimensional or more. And as a result, you have gradients in how you shield the plasma. And those gradients create, again, perturbation of the electromagnetic field. So we see propagating O modes that are created in the base of this very dynamic gap. So this sort of relates to what Roger and Pawan have been saying, that there are these strong time-dependent electric fields that are formed, for example, in further away in your model where the waves dissipate. Maybe it's related to what we're seeing in the gaps close to the star. I'm not sure that's the mechanism we need for FRBs. If I wanted to bet, that would be more on the current sheet emission and plasmoids. But that's what I know based on radio pulsars. And one comment I wanted to make about these alpha N waves and breaking of alpha N waves. I thought about, well, this sounds like a cool idea. Should I simulate this? And then I thought about the following, that we kind of did simulate this before. If you want to create a very strong alpha N wave, you twist the star and it launches a huge alpha N wave. And that's what we do when we start rotating pulsars, right? When we start forming a pulsar magnetosphere, we spin it really strongly. There is no just dipolar field outside, strong alpha N wave propagates. What it does is when the field strength is stronger compared to the background field, what it does is it just changes the magnetosphere. You open the field lines, you reform the magnetosphere, you form a wind. And I'm afraid that's what's going to happen. When this magnetic field is going to become very large compared to the background field, instead of just deciding that it's giving up and creating, just shorting out, it just will change the structure of the magnetosphere. And these alpha N waves carry charge with them. So I think they will just open up, let this thing leave, and nothing bad will happen. But this needs to be checked with a simulation. So I'll stop here.
So Wenbin, you had your hand raised briefly, I saw. Why don't you address, and then let's just turn to audience, because the time is we have very limited amount of time, and we should have a sample of questions from the audience. So Wenbin, briefly, whatever it is that you were going to address.
Yeah, I want to address Yuri's question on the plasma effects on the radiation. So indeed, it's very important, but just for O mode. For X mode, as Roger is very clear, so for the X mode, the refraction index is exactly 1 when the B field is infinite. So near the surface of a neutron star, the X mode would just propagate as if in vacuum. There is not much of a plasma effect. But the O mode, I agree, or the alpha N wave is strongly affected. That I agree. Yes.
Let's turn to the audience. Let's take. Sorry, Roger, you were going to say something.
It's going to put a question on the table. In addition to simulation to explore what's going on here, is there any hope with E-beams in laboratory, places like SLAC and so on, where you've got undulators? Can you actually learn something from? I mean, there's a lot of physics that goes into those, but also maybe doing more stylized experiments that might explore some of the effects that Wenbin and others talked about.
Let's turn to the audience. Let's take some number of questions, and I would. I saw you first, Ido Berger.
The question is related to the models where the efficiency is low and there's of order 10 to the 46 ergs of total energy. So if it's in gamma rays, I think that's kind of hopeless to see. In the optical, do we expect, so I understand what's the time scale that's expected for the optical emission? Is it comparable? Is it a millisecond time scale?
It would be something of that. No, go ahead, Ali, go ahead. You go ahead.
I think in all these models, the timescales are comparable, but you don't have to search for millisecond pulses in the optical. Because even if you are integrating over a few seconds, you should still be able to see them quite far away. So the total energy is.
I ran that number quickly. I mean, if you're integrating a typical integration in these optical surveys like ZTF is something like 30 seconds or a minute, you smear out the signal enough that even at 100 megaparsecs, which is one of the nearest FRBs we have, you're down at the level of magnitude 21, which is at the very threshold of a survey like ZTF. So again, I don't think it's trivial. It's probably easier than gamma rays, but it's not trivial with the surveys we have right now.
We are going to turn to, yes, Suliam.
Somewhat related question also for Ellie and others. So in the absence of, say, an optical flash or an X-ray detection, is it useful to dig really deep into the luminosity function of a nearby repeating FRB? So if the energy budget in radio is dominated by micro-Jansky bursts, which you can't see, but you see that it's still rising at millijansky bursts with fast or something, is that informative or you don't have enough?
Well, I'll let the others answer, but I think yes. I think that the best bet is to look for the nearest events or the brightest events, so that you can have a reasonable chance of detecting the other components.
So we have, okay. We have a number of questions also, which is being posted by, online questions. So if you want to turn around and answer, not you, just you, Ali, but other members of the. No. You can turn around. You're welcome to turn around and move. So anybody would like to address these questions?
What is chi here?
Chi squared voltage. I'm reading it below, but I assume you mean open.
So.
The observers agree with the assertion there about the counts.
Yes. So go ahead. Please go ahead. First one, yes. Highly uncertain, yes.
So I wouldn't really consider this somehow discrepancy a discrepancy yet.
That's what I thought.
X-rays, yes.
Yeah, that's what. Vicky, you had a question or a comment or something?
Well, it was a comment and then a question, but it's not related to what's on the
That's
board.
okay.
So the first comment, first of all, I'm still reeling from Roger's comment yesterday about how the galactic magnetars are, quote, boring. And I am hoping that Nanda will school you in that regard later today. But nevertheless, I think what's important is that none of the magnetars that we know of, either from their emission properties or their location, all in the disk of a spiral galaxy, look like the magnetars that you're talking about. So I'm coming back to are they magnetars? And so I do feel that there is a little bit of a tooth fairy there that you have to imagine, a very special kind of magnetars. We always call them magnetars, but I always think of them, they're weird magnetars, number one. Number two, we know that some of these FRBs are in not young galaxies. We heard that from Ryan Shannon's talk, and so you need that accretion-induced collapse to create a magnetar. Okay, that's another tooth fairy right there. And so now I'm coming to my question. We also now know that at least one of these sources, and one of the ones that's fairly early discovered, so you can dismiss it as an oddball, but it has periodic activity, and I haven't heard that today at all. And so now you want weird magnetar created by accretion-induced collapse. Okay, not in that case, it's in a spiral galaxy, but nevertheless orbiting in 16 days. So isn't that a third tooth fairy, and how many are we allowed before? So I'm rooting for Chris Thompson also, Roger, in that regard.
It's a very interesting sets of points here. Brian?
Well, no, I mean, I would say one thing probably talk about this afternoon. I mean, it's not true that there aren't any stars forming in old galaxies. So I think if we have a few, if we start getting many, that's going to be an issue. But it could be also there's young population. I was also say, just to go back to Andre's talk, we think that magnetars when they're born could be very, very different properties. Jin, who's wrote this question up here, has worked on, arguing that if you have very strong magnetic fields at birth, that the rate of magnetic flux out of the core is controlled by ambipolar diffusion and could be much faster. So they could be flaring it. Principle, magnetars with even stronger magnetic fields than the galactic ones could be flaring at a much higher rate. So I think I'm saying theoretically we have some expectation that there could be diversity. So I don't know if that's the paper was before the event, so I call it prediction, but yeah.
Tooth fairy.
Yeah. So okay. Anyways, I forget what was the third tooth. Anyways.
So there is the third one was, I think, very interesting CHIME result of 16-day periodicity. So that's something that so the panel, would anybody on the panel like to take up that question? Periodicity. So there is a CHIME claim of 16-day periodicity for one of the repeaters. Is based on, sorry? There's a huge jitter. It is a quarter of a phase. So in that regard, yes. Radio pulsars would also not be periodic in your Yes, but I think they have more than 15 periods of observed. So that could be one way out of it, sure. Anybody?
Is this predicted? Has that period been predicted in the data?
Yes.
Pulsar process. No. We think there's some quasi evidence.
Was it predicted in the first half of the data and then continued for the second half?
No, not yet.
So that would be definitely worth will give more confidence. Yes. But the good news still is that they will have more outbursts from this source, and so we will know. It's just it's a question of time. Whenever it may be a month, maybe 2 months, but we will know the answer to that one. So that will get settled. Looking at the time, looking at the.
Why do you think that's a tooth fairy? Let's say that is of a binary system. Why is that a tooth fairy? I mean, most massive stars are in binaries, and so you would expect most neutron stars to be in binaries.
Most pulsars are not in binaries. It's like 2%.
I think that it could be an oddball, but if they were all in binary systems, isn't that a little odd?
It has to be in a dirty binary.
Okay, we should have a number of other points of view, questions raised. Bing Zhang, you have been very patient. You had a question or comment.
First, go back to what Wiki just said. So oddball. So for this guy, why we think it's oddball? We only have like one case that really monitored this long. So maybe it's not an oddball. So
well, it's 121102 has been monitored for much longer,
but
and people have looked for periodicity.
Search for period for such a long period, right? So anybody?
Yeah. Please go ahead. Yes.
Periodicity that's been looked for is a rotational periodicity between the bursts.
I know. Yes.
And so that's on the scale of like seconds kind of scale. And because of the way the observing works with random spacing, it's very hard to go back and look for something like a 4-day window in 16 days, even though we've always talked about the bursts seem to be sporadic and they seem to be on sometimes and not on at all. So there are different things that are being mixed in under periodicity.
You try and have a lot more repeaters, so maybe you guys can find more. I don't know.
But time also has the benefit of the regular observing pattern where it's constantly monitoring.
So, Jason, you had a question
or
a comment. Oh, you have a follow-up, quick follow-up?
No, I actually have separated question. But if this is related, maybe go on. So I have.
Go ahead and ask your question, and then we'll go to Jason.
question actually to the panel, to Anatoly. So it's a very different question.
If it is very specialized and not of general interest to the audience, then I suggest discussing it over lunch or tea. If you think, and I'm going to just.
But just can I preempt your question? So there are pulsars with planets, right? And as you probably, there are also asteroids. But so what's wrong with that? Just add epicycles to the previously incomplete models, and you're done.
Yeah.
Okay. Okay. All right.
What's wrong with
yes.
asteroids?
Yes, Ali.
Can we also suggest a topic for
Well, there were other questions and topics, but I think we have turned to the audience, and we are just taking kind of broadly now to anything that we have got. Jason, you have got something.
Yeah, so I just wanted to ask the panel about their thoughts about the drifting subburst to lower frequencies, sometimes known as apparently this sad trombone effect. I think that's really, really diagnostic. Of course, there's analogies with solar bursts as well, and I was expecting to hear more about that today because it really is quite different than what we see in pulsars, and it's quite obvious that it's quite characteristic
So certain
of.
number of papers have been written, number of people, well, I don't know about the panel, but Brian, you have worked on it. Lorenzo, wherever you are. Lorenzo, you have worked. So you want to take that up? Lorenzo, you want to take that up?
You already summarized it well. So, I mean, at least within any shock-dominated scenario where the shock is sweeping up the external medium, you would naturally expect a drift of the spectrum just because the plasma conditions are changing over time.
With really discrete, almost regularly spaced gaps between the subbursts as well.
Well, that will...
And also the drift changes with frequency, observing frequency as well. In a systematic way.
That will have to be quantified better. It will naturally depend on the intrinsic synchron maser spectrum in the case of the synchron maser operating at the shock. Because as I said, the frequency structure intrinsic to the generated spectrum as well will impart drifts in the observing band that are just dependent on the fact that the spectrum is not a broadband spectrum, but it will have like line-like features that will just sweep through, and potentially there will be a gap because there are just two lines. The first line sweeps through, and then you don't see anything, and then the second line comes in the observing band, and you're seeing it. So anything generic that could be assessed in terms of like these gaps on the observational grounds would be useful to see whether there is a preferred plasma condition such that the spectrum is most likely to induce those gaps. But I think the generic statement about the fact that any blast wave will be producing emission to lower and lower frequencies with time, and so producing the drift, I think that's fair to say.
Yeah, I just wanted to comment briefly on the frequency drifted. Sorry. The drift at different frequencies. So the picture is you have a blast wave. It starts off at some t equals 0, and everything's evolving as a power law time with respect to that. And so, so the two predictions of that are that the drifting rate will, so basically the burst will actually be longer at lower frequencies because it's going out to larger radii, and that the drifting rate, say it's a power law, I think the drifting rate goes down to lower frequency. We can talk about it, but there's a prediction. Because you're saying that the thing is sweeping as a power law in time relative to some, flare, then that predicts that the duration, that the sweeping rate will become lower at lower frequencies.
So, Tandulkar and then Starfini.
So I had a question about. So I was briefly discussing this with Brian earlier. Can this, so the PIC simulation seem to be fairly advanced. Can you actually forward model a complete what an FRB would look like at the end of this thing? Because I think the deviation from a frequency to the -2 dispersion measure is can very sensitively be measured by us. So the fact that we don't see deviations from frequency to the -2 is, I think, very discriminating for this model.
I'm not sure I'm entirely capturing. I mean, there's Newton -2 is also coming from propagation effects that have to do with not just the place where the emission is generated, but the potentially propagation
Absolutely.
in the supernova ejecta, the surrounding host galaxy. I mean, are you?
So if there is a nu to the -2 dispersion, right, all of that is additive and that can be corrected. But if you have something different from a nu to the -2, so where you have a wind or a constant density profile, if you get a power law which is different, that can sensitively be measured. That any deviation from a nu to the -2 can be sensitively measured, and it can constrain the k factor in your density profiles. Yeah, but I.
But deviation from the nu to -2 has to do with like omega equal to the plasma frequency, right? If you're close to that limit, then you're expecting deviation from the cold plasma dispersion relation. So, I mean, in that sense, yes, but not in the sense that you're probing the medium. I mean, any density you have outside, if omega is sufficiently far above the plasma frequency, will be will be giving you the nu to the -2 as like vanilla.
Yeah. So let's go to Sterl. Sterl. Great. Let's have the panel address that, Roger.
As they say in theological circles, there are sins of emission and sins of transmission, and I'll vote for the second here.
Second one, yes.
I think that there are modes where you can get away from quasi-linear propagation in the rather strong field extreme environments that you have around these sources, whatever they are. And I'm not sure how prevalent the circular polarization is. I know there's the 130% case, but I don't know how common it is beyond that. But I would say that's not going to rule out too many of these models in practice, would be my guess.
My question was whether the models in the strong field it seems really hard to avoid having linear polarization.
Yeah, that's correct.
And
yes.
so I guess my question was whether does everybody agree that propagation is the only way to get circular, or are there other ways?
Well, somebody has to talk to the people in the wind should. I would have thought they had other options.
I think that I'm not trying to advocate a model, but in the weakly magnetized case, you do get quite different growth rates for different for right-handed and left-handed circular polarization. So in principle, you can get strong circular polarization in the weakly magnetized.
Since we have a number of observers here, how many cases are there where you are confident that you are seeing circular polarization? Yes. We have only a few minutes left, really, and I would like to just pose a question to the panel. What kind of observations is needed to be able to understand the FRB emission mechanism? What do we need? You, theorists.
Well, multi-wavelength and multi-messenger especially, and in the spirit of falsifying some of these models, I think that is where I guess we're going to get the next meeting is going to have fewer models to talk about.
Other views, other point of views.
Maybe
Yuri?
Very important is true duration of the bursts before scattering all that.
So that is corrected for, and if you look at many of these papers, they correct for the IGM and IASM scattering, broadening, and for many of these cases, the broadening is small. Observers can correct me.
Well, you need to be very careful with that as well, because some of the profiles have frequency-dependent shapes that you can fit out as scattering.
Some of them do, but the question is that there are also cases where you don't see lambda to the power -4 or 4.4 broadening. Yes?
I think very little is known observationally about the lower limit on intrinsic widths. So when we dump voltages and we coherently de-disperse, we see 10, 20 microsecond structure, but that was an FRB detected with a millisecond backend, right? So we don't know if there are 25 nanosecond FRBs, and we should. Well,
what are you defining as an FRB? Are you defining it as a single? I mean,
yeah, I would say I would include microstructure. Yeah, I would include microstructure.
What?
Include all of those. I guess the distinction is the width of a subpulse versus the beginning to the end of a.
No, there are examples of very narrow individual FRBs.
Anatoly.
What would help me is to know which ambulance to chase, because observers really like their unique objects, and theorists like a spherical cow object. So if you could tell us what's normal and what's outlier, that would be really, really useful.
On that note, should we thank the panel? We have used up the time, and it's lunchtime, so we should wrap things up. Let's thank the panel members.